So let me first welcome today Mr. Nikhil Bhamare. Mr. Nikhil Bhamare is a founder at CFD Baba Simulations Private Limited, and he is also an esteemed member of the advisory board of the CFD team of FOSSEE. So let me just introduce him, and then we can go ahead with the lecture session by Mr. Nikhil. So Mr. Nikhil has a bachelor's in mechanical engineering and master's in thermal engineering. He has been introduced to CFD during his masters. He had to spend a lot of time gathering the information that is spread across various resources to perform successful CFD analysis. He now wishes to help beginners in starting their CFD journey smoothly. Mr. Nikhil has solved various academic and industrial problems from all over the globe related to internal flows, external aerodynamics, heat transfer, porous medium, species transport, and multi-phase flows. He has the experience of training more than 4,000 students worldwide. He wishes to spread as much CFD application knowledge as possible to help new CFD enthusiasts to start their career with a sound knowledge of CFD. So over to you, Mr. Nikhil. Welcome once again, and you can start the session now.
Yes, thanks a lot, Payal man, for the introduction, and a very good morning to everyone. So today we are going to look at this topic: key skills for CAD and meshing in industrial applications for CFD using OpenFOAM. So I'll start with my first OpenFOAM problem, and then what skills do students require, or even freshly graduated people require for industry. And then we'll look at a live industrial case study today. I'm not going to bore you with PPT. And then we'll look at what after learning skills, and then we'll close the session with some conclusion. So first point is the first OpenFOAM problem which I solved in industry. So I started using OpenFOAM 8 years back for solving one industrial problem directly. So my first CFD tool was OpenFOAM, which was used for industrial application. And at that time, I struggled a lot to get the simulation done because industrial simulations are complex due to many phenomenons occurring together inside the CAD model or our CFD domain. So after I successfully completed that problem, I started this channel named CFD Baba, and I started it on YouTube first, and slowly it started growing. And now it has grown such that it is almost rank 15th in the entire globe of people who promote CFD. So it is now ranking with many top global OpenFOAM promoters, and I have more interest to promote OpenFOAM in India because CFD is done a lot in India, and if we can use OpenFOAM, then it would be a huge benefit to the cost required to run CFD simulations. And as you can see, this list was posted by Simon Fisher on LinkedIn, and he showcases all the people who talk about CFD. So in my last industrial visit at IIT Bombay, I had shown these things. However, this time we have a lot of new participants. That's why I am reiterating some of the things which are achieved. And they call it influencers, people who talk about CFD with passion. and this is the latest list. So now, after 8 years of industrial experience, I have started CFD Baba Simulations Private Limited, which is a CFD training, consulting, and software development firm. And our mission is to empower CFD users worldwide with CFD mastery. But why do we want to do this? Because many of you might have ran CFD simulations, and you know if you give wrong input, you will always get wrong output. So, if you don't know what input you are giving, then it will create lot of wrong outputs, and that will be just wastage of time and energy. So that's why CFD users should at least know what they are doing, and that will reduce the trial and error a lot, which can give a huge benefit in the time and cost required for CFD simulations. And we do that through providing custom CFD tools, technical support, training, consulting, and also innovation. And the vision is a future where CFD is affordable, powerful, and accessible to all, starting from startups to also space agencies. Because right now, CFD is expensive and it cannot be accessed by all very easily. So, to fulfill this vision, uh, till now we have delivered 200 projects and trained more than 5,000 engineers across 15 different countries. And I am also advisory board member at FOSSEE, IIT Bombay, and FOSSEE also awarded me the Mentor of the Year award, for which I am very thankful in recognition of the mentorship that was provided. And now let's look at the first industrial problem which I faced in OpenFOAM, which I was talking about. So, for industrial simulations, you always need to simulate many models together. Like in this case, first there was a fan boundary condition, then there was heat generation, then there was rotation of the coupling, there was porous medium due to heat exchanger, and there were also porous medium at the bottom for openings. So many models need to be simulated together in order to simulate a real industrial CFD problem. So this was the thermal housekeeping of a wind turbine nacelle. So you guys have seen windmills, and these windmills have three blades at the front, and behind those blades there is this room-like structure. So in this room, when the blades rotate, the shaft also rotates. It passes energy to gearbox. Then the energy is transferred through coupling to the generator, and finally, the electricity is passed down through the tower on which this nacelle is standing. So there are wires to pass down the electricity, and then it is collected at the bottom. So this is how a wind turbine works. And I had to simulate the heating of these components. And the problem was that this coupling was getting heated up above the above the reference temperature or recommended temperature. So uh, the system in wind turbine is such that if a component overheats, it reduces the speed automatically of the wind turbine to cool that component, and that reduces the energy output. So we wanted to design a system such that the cooling of this coupling should be efficient. So there were four fans, two at inlet at the behind the nacelle and two at the top. So this was the mesh generated using Snappy Hex Mesh. And you can see how we improved the design. So in original design, you can see that the duct of fan 4 and fan 3 is not extended down, and now it is extended down, and it helps to suck in the hot air coming up from the fluid coupling. So this is the design modification suggested, which worked to reduce the temperature of fluid coupling successfully below the recommended value. So all this took me a lot of time and effort to complete, because 8 years back there was no tutorials and very less knowledge about OpenFOAM CFD on internet. So that's why I started myself contribute to the knowledge of CFD on internet. So this brings us to you. What skills do you need if you are seriously trying to pursue your passion in CFD industry? So you need a combination of many skills together. So we have technical skills, we have domain knowledge, and we have practical and soft skills. So in technical skills, you need to have the knowledge of the tool which you are using. So the CFD tool can be anything, it can be any software, but you need to have hands-on practice with the tool. You need to be able to clean the CAD model, mesh it properly, set up right boundary conditions, and monitor convergence. Next, you need domain knowledge. That means you need the theory knowledge. So for that, you need to read books on thermodynamics, fluid mechanics. And finally, you need practical and soft skills. So practical skills means that you need to have some uh, skills that can automate your work, which can be using Python to automate your work. And you also need to have good soft skills to be able to present the report to your customer, because in the end you just don't send the files to the customer and say that have a look. Most of the times the people who are going to read your report are not CFD people, and they don't understand CFD. So you need to have soft skills such that you can make a common man understand your CFD results. So today we are going to look at live industrial case study of a data center, which is a rapidly growing infrastructure in many parts of the world. So this is what a data center looks like. There are many buildings, and inside the buildings there are rows and rows of server racks. So these are just computers, and they are processing the data which is sent to these data centers. But during all this, lot of energy is consumed for running this infrastructure. And almost 40 to 60% of that energy is used in cooling of this data center. So since it is continuously running, it generates heat, and it releases heat into this room, and that heat should be removed successfully in order to keep this data center room uh, cool. And that's why there are different mechanisms to remove heat from the room. But all those mechanisms require 40 to 60% of the total power to just keep this room cool. And why do we want to keep it cool? If it overheats, it catches fire and starts burning, and then the fire may spread and burn down the entire facility. So we want to avoid fire at any cost, and for that we need to keep the temperatures down. So for that, one of the concepts is hot and cold aisle concept, where we have server racks facing So the front end is facing together and the rear end is facing together. From the front end of the server rack, cold air is supplied into the room and it is sucked out by the CRAC unit, which is computerized room air conditioner, which can control the temperature and flow rate of air in the room. So basically, what it does, it takes in the hot air and then it sends out cool air from the bottom, and then that cool air comes out from these grills in front of the front end of server racks. Then the cool air gets sucked in, it transfers the heat with the server rack, and then the hot air goes out from this pipe back into the CRAC unit, and then again cool air comes out from the bottom, and this continues. So this helps us to keep the zone in front of the server rack cool, and the zone behind the server rack is hot region. That's why it is called hot and cold IL concept. And the benefits of doing CFD is that, as you know, we have total 40 to 60% power used in this. So that means huge cost, almost 40-50% cost goes in designing the cooling system of this data center. So in that, CFD plays a very crucial role because it can predict the hot and cold regions even before we build the real data center by investing millions of dollars. So that's why if you are even able to optimize the percentage of cooling by 5 to 10%, then it would result in thousands of dollars saved for each data center. So that's why this is important to study. And let's now start with the case study. So I have this step file of CAD model ready with me. So I'll be simulating this in OpenFOAM. However, I'll be using this tool, Bind Simple Foam CFD Forge V2412. I'll just open it. And here we have the GUI of Bind Simple Foam CFD Forge. So you can set OpenFOAM path here, and I'm using OpenFOAM version 2506, but you can use any ESI version using CFD Forge. And you can set the ParaView path. So currently I'm using ParaView 5.13. So you can use any path. And now we need to select the working directory. So I'll use this same working directory, this PCD IITB industrial case study, copy it, and I'll just paste the path here. And this folder is selected, and I'll select the folder. It says, do you want to create new case? Say yes. And now the template case is extracted at the location. So now you can see we have 0 constant system folder, which are required for OpenFOAM simulation. And now we need to bring in the CAD model. So this is just a small demo how we can use this tool CFD Forge. So for this, I will use a dummy CAD model first. So I'll go in the resource files, which is already provided, and I'll go to demo CAD models, and let's use the multiple outlet pipe. And I can select all the STL files. So it supports STL files, and you just need to name the boundaries, click on open, and it has imported and combined the STL files. So let's analyze the geometry to view the dimensions in X, Y, and Z direction. So the pipe is 1 meters long, 0.2 meters in Y, and 0.95 in Z. So it is quite a big pipe. And we can click on View CAD, and it will open the CAD model in ParaView software, which is again open source tool for post processing the simulation results. So I can hide in the boundary STL and I can only turn on CAD.stl. And you can see this is the geometry. We have this inlet face, we have the walls, and we have the outlet. So we have 4 outlets. And now we need to mesh this model. So to mesh it, I can simply enter the minimum cell size, maximum cell size, and a number of layers and the number of processors I want to use. So let's try to mesh with default settings and see what we get. And then we'll modify the mesh as required. So I clicked on save mesh settings and generate mesh. And it generated a mesh with 25,000 cells and max QNS is 2.89. So recommended is below 4. So the mesh quality is fine, but we cannot just trust the quality. So we will click on view mesh, click on apply, and we need to visually inspect the mesh. So you can see here that it has created 3 boundary layers, but the mesh is very coarse here because at the outlet only 3 or 4 cells are created, but we need more cells. So let's decrease the minimum cell size to 0.05, which is 5 mm, and again save the mesh settings and generate the mesh. So it is using Snappy Hex Mesh to mesh this CAD model. And again the mesh is done, but this time cell count is 68,000. It has increased almost 3 times. And max QNS is below 4. So to just view the new mesh, simply click on the refresh here and click on last frame button. And now you can see that the mesh is refined and created properly at the outlets. We can view the cut section by taking a plane normal to Y and viewing the cut section to look at the boundary layers. So 3 boundary layers have been created properly across the domain up to the outlet. Now we need to solve this simulation. For that, we need to define the material properties. So the default properties are set for air, and we need to enter the gravity direction, which is negative y in this case. And then we need to specify inlet velocity, direction, pressure at outlet, temperature at inlet, K and epsilon values, and turbulence model. So let's set the inlet velocity to say 10 meters per second, but I need to view the direction of inlet. So the flow will go in negative z direction. So I will set it in negative z as minus 10 meters per second. And for inlet temperature, let's keep 300. And K and epsilon values can be calculated by using the formulas for K and epsilon. So it is provided in the resource files folder, this turbulent calculator Excel. And you can calculate the value of K and epsilon by providing the hydraulic diameter, speed of fluid, and the turbulent intensity. So I have already calculated it. So for 10 meters per second flow and hydraulic diameter 0.1, I have to use this K and epsilon value. So I'll simply copy paste the values for K and epsilon. And I'll set the model to K epsilon turbulence model and just click on save setup. We can close the Excel. And now I'll go to solve and I need to solve. So I'll enter 1000 iterations with right interval of 100 iterations. So after every 100 iterations, it will write the results. And if you go to monitor plots, you can visualize the residuals, how your solution is converging for velocity, pressure, energy, K and epsilon. And once 100 iterations are completed, it will write a data folder of 100. So we can view the results while the simulation is running. Go to post process and click on view results. And it will open ParaView with the results loaded for the time steps that are solved. So here we can see pressure. We can view the cut section again to view flow inside the pipe. We can see this is the static pressure. We can view velocity, which is 10 meters per second coming in at inlet, getting spread across inlet and outlets. We can view temperature. It is almost same, 300 to 300.1. Then we can view Y plus, which is the maximum Y plus is 156, and we are using K epsilon model. So Y plus should be between 30 and 300. So we are using correct Y plus values with the help of our boundary layers. We can also inspect the total pressure and the static pressure. And here in the monitor plots, we also have pressure monitor, which tells us the value of pressure at inlet. So if this plot becomes stable, that means our solution has become steady state. So these are all the things you can do with CFD Forge. However, this tool is not built for toy CAD models. So now we will simulate a real industrial case of full scale uh, data center. So I can abort this simulation and it will stop. So it has run up to 800 iterations just on a single core. And I can use this option clear time folders, and it will clear all the time folders. And now I can start with my new CAD model. So let's import another CAD model. And this time I have this folder named CAD where I have the STL files. But I don't have them right now because we will prepare them using FreeCAD. So I have this FreeCAD open. I'll open parametric part. And now I need to import my step file. So this is the step for CAD preparation. And I can go to file, import, and I can paste my path and double click on step file, click on OK to import my step file. And here you can see that I have my step file, which is a single solid. I mean, it is a fluid domain of the air extracted inside the data center. So how to view it? Right click and go to toggle transparency, and you can view inside the CAD model. So this is a full scale CAD model. And we have many server racks here, and we have two CRAC units on the left, and this is a raised floor data center. That means cold air will come in from the bottom, which is a false basement kind of height, and then hot air will escape from this false ceiling back into the CRAC, and then again from the bottom of CRAC cold air will come in, and then again it will come out through these grills provided at the floor bottom. It will carry heat from the data center racks. It will go up through these openings provided at the top. Then it will go here, and then it will again go back into the CRAC from the top. So this is how the circulation of the air is going to be. And we need our STL files to run this in CFD Forge. So how can we do that? For that, we have this option. We can go to part, workbench, we can select top air and we can go to part, and here we have this option to make the compound explode. So I'll go to compound, explode compound, but you can see it has just created one single. So I'll again select it and again go to part, compound, and explode compound. And now you can see it has created each face separately for our CAD model. So now we just need to name our boundaries. So I'll name inlets and outlets. So I can select any face and press space to hide it. And this way I can hide the ceiling. And now we can see inside the room. So here we have the CRAC inlets. So I'll select this face. I'll press Control on my keyboard and I'll select the other inlet face. So both are selected. And we'll use this tool union to make them into a single part. And we will name them as CRAC. These are actually outlets because air will get sucked in from the top. So I have named it as CRAC outlet. Next, we will name CRAC inlets at the bottom. So I'll hide this floor. And here we have the inlet face. So I'll select this face, press Control, select another face, use the union tool and name it as CRAC inlet. I'll hide these, which we have already named. And now we need to name our server rack inlets and outlets. So I can hide the walls, and here you will be able to see our server racks. And this is the inlet face of the server rack. Air will come in from these bottom openings, and then cold air will come in from bottom and get sucked into this face, and then it will heat transfer through the rack and it will come out through the back face of the rack. So this will be our hot air inlet into the room, and this will be our cold air outlet out of the room through the server rack face. So let's name them accordingly. So here we need to name the faces of hot server rack. So I'll select the faces, 4 faces, by pressing Control on my keyboard. I have selected all 4 faces. Make them union, press yes, and we can rename it by simply pressing F2. And we will name it as hot air inlet for what? Rack. So I have named it as rack hot air inlet into the room. And finally, we need to specify the hot cold air outlet. So from where will the air get sucked into the rack? From these faces, which are in front of the grills at the bottom. So I have selected these faces, make them union. Yes. And I know it might be fast, but you can watch the recording, which will be provided. But right now, you at least are getting to understand what we are doing and what is the actual process you need to do in industry. So we have named the rack cold air outlets as well. And cold air will escape from our domain through these faces. So I'll hide these. And now whatever is remaining is nothing but our remaining walls. So I can do one thing. I can hide the exploded part and again show it. So it will show all the faces. Then I'll just hide the ones we have named. And now whatever is remaining are the walls. So we can select everything else and we can combine it using union tool, and we can name it as walls. So we have named our patches walls, inlet, outlet, and now we are ready to export the STL files. So I have this macro to export STL, and I can simply select the location. So I'll export my STL here in the STL folder, and I'll paste the location, and it will select this folder. And if I view the Python console, it will show me that the CADs were exported, and we can check them here. So you can see it has exported all the CADs, and it has also combined it into a single CAD named CAD. Now we are ready to use CFD Forge. We have our STL files. So we just need to select the boundary faces, not the combined CAD model. Click on open. It has imported 5 STLs. Analyze the CAD. So it is a full scale model. The length is 10 meters, width is 6 meters, height is 4.37 meters. And we can view our STL files in ParaView now. Click on apply. Hide all the boundaries and just turn on cat.stl. We can make it solid color, and we can reduce the opacity to view inside and just inspect that everything is fine. I can see that everything is imported correctly from FreeCAD into STL. And now we are ready to do our mesh. So this is a very big problem. And we need to be careful about mesh size. We can't create a very fine mesh. So I am going to showcase with coarse mesh due to time constraint, and also the objective is not to simulate accurate simulation, but rather to show the procedure behind simulating it. So we can enter a minimum size of 50 mm and max cell size of 100 mm. So why am I choosing this? So this is the meshing strategy. So here I can see I have this small face here, which is the smallest face in my geometry. So I need to measure its dimensions. And if I try to measure it here, how can I do it? I can use this create ruler option. I can click on a point here, and I can again press P on my keyboard to create another point. Click on apply, and it will show you the height, but it is not showing it accurately right now because I did not click using the normal view. It is something else only. So for that, you need to measure it in a normal view. You can go to camera parallel projection. You can set the view, and you can see it was measuring something else entirely. So let's select correct height. So press P here, point the mouse, press P, again press P on the surface. You can adjust it, click on apply. So it is 0.1 meters, which is 100 mm. So we need at least 2 cells across the smallest face. That's why I am using 50 mm for the minimum cell size. Now let's look at the maximum cell size, why I am using 0.1, which is 100 mm. So let's see the dimension of the room in the longest length, which is the ZX direction. It is 10.5 meters. So I need at least 100 cells across the length. So if I divide this by 100, so this is 10 meters, and it will be uh, basically 100 mm if I want 100 elements along the length of 10 meters. So I'm using max cell size 0.1. And now I need to select location in mesh. So it can be any point inside the mesh. How do you create it? So I'll delete ruler. Press Ctrl and space on your keyboard to open the filter. Search for point source. Double click on it, and it will create a point in randomly in the domain. So now we need to place it such that it will be inside the fluid domain. So this is where my fluid domain is going to be. Air is going to flow in from this server bottom, I mean CRAC bottom. Then it will flow through the bottom of the room, come out through these grills, and then it will go up, and then it will escape through the outlet grills. Then it will again be sucked in back into the CRAC units. So this is the fluid domain and my point is right in the middle of the fluid. So it can be any point anywhere. So I can just copy paste the coordinates or enter them. So this is minus 0.01. It is fine. Then next is minus 0.268 and it is 1.11. And I'll use zero number of layers because of time constraint, but we can add layers like I displayed in the multiple pipe outlet. And I'll use 4 cores to make it fast. So I'll save the mesh settings and generate the mesh. Let's see how it generates the mesh for such a big CAD model in such less time. So it has now created 4 processor folders and it has decomposed the mesh. Now it is creating a snappy hex mesh. Now it is reconstructing the mesh. It has finished meshing. And it has created 470K cells with a max skewness of 3.74, which is below 4. So this quality is acceptable, but we always need to inspect the mesh visually to be sure. So let's view mesh. Click on apply. And we will turn on surface with edges to view the mesh. And this is the snappy hex mesh. And you can see that it has captured everything. Let's look at those grills. So yes, at the grills, we can see it has exactly created 2 cells like expected because the total length was 100 mm and we gave minimum size as 50 mm. So it automatically detected the smallest faces and applied 50 mm there. We can also view the cut section by taking a cut section, let's say along Y. You can turn off triangulate slice to view the mesh without the crisscross triangles. This is the actual cut section. And you can see the smart automated workflow of CFD Forge has refined the mesh where it is necessary. Like in this case, the air was going to flow out from here. So velocity is going to increase here. So we need some refined mesh in order to capture that velocity increase accurately. Same thing at the bottom from where the cold air will come into the room. So our mesh is created and now we can solve it. So I'll use the default properties of air. I need to select the direction of gravity. So gravity always acts in downward direction, which is negative z. So I will enter the direction of gravity in negative z direction, minus 9.81. We can use the inlet velocity as any value. So let's use 100 because we will change it later. Outlet pressure will be atmospheric pressure. Let's use room temperature of 300 Kelvin, which is 27 degrees Celsius. And we can change back K and epsilon to their default values of 0.1. And we'll select turbulence model as K epsilon for this case as well. Click on save setup and the setup is saved. But before we click solve, we need to change the boundary conditions of inlet. So how can we do that? We can go to resource files and here you see we have this inlet boundary condition file. So we can open it and to change the boundary condition of our inlet, we can go to 0 folder U file and open it. And now you can see we have our CRAC inlet and rack hot air inlet for which we want to change the boundary condition. So we want to specify flow rate, volumetric flow rate on those faces. That's why I will copy this boundary condition, flow rate inlet velocity. And I'll replace the boundary condition of CRAC inlet and rack hot air inlet. So I'll use a flow rate of 8.9 for CRAC inlet, and for rack hot air inlet, the hot air will come into the room at 3.4 meter cube per second. Next, we want to change the temperature. So at CRAC inlet, cold air comes into the room at let's say 20 degrees Celsius or 15 degrees Celsius. So we can either use 288 or 293. So for this case, I am using 20 degrees Celsius coming out from CRAC. And CRAC outlet, we will keep initially at room temperature, which is 300. And then rack cold air outlet, we want it to be initialized with the cold air temperature, which is 293. And rack hot air inlet, so the hot air coming in from the rack faces, let's assume it 40 degrees Celsius. So how much will it be? 313 Kelvin, right? And we will save this temperature file. And now we are ready to run the simulation. So I can go to solve, and let's write the data interval at 20 every 20 iterations. Let's solve just for 500 just to visualize the initial flow, and I'll click on solve. But before solving, I need to change something in the control dict file. So I can press abort here, and it will abort the case. So the thing is, in system folder, we have control dict, and here we have specified to measure inlet at, I mean pressure at inlet and outlet patch. But since we have multiple patch right now for inlet and outlet, we don't need it. I'll delete it. And it will take time to write those values. That's why, due to time constraint, I have deleted it. And now we can clear our time step folders again, and we can try to click on solve, and it should start the decomposition of the case. So it has created 4 processor folders, and then it will start the iterations, and we can monitor them in the residual plot. So it has started, and it will write the data after every 20 iterations. However, this is in parallel, so it will write the 20 folder inside the processor folder. But we can view the results while case is running. For that, I will close all the other paraviews and go to post process view results. So how to view results for such big case, because we cannot just show one plane, right? It would not explain anything. So that is the next skill you need for post processing and making the common people understand. So I'll reduce the opacity, and I'll create some planes to visualize the results. So we have this case.foam, and now we need to create the planes. So how can we do that? Use this plane option. And we cannot just create a single plane for this complex CAD model. We need multiple planes. So we need one plane at the center of CRAC and the inlet ducts at the bottom. Click on apply. You can see these partitions are due to the decomposed mesh which we created, but we can ignore them for now. And I'll create another plane at the center of second CRAC. Click on apply. I had to first select case.foam and then create a new plane, and then place it and press apply. I can hide the plane bounds. Next, I need to create a plane which will show us the velocity coming out from the bottom in horizontal view. So I'll select Y, and I'll just take a plane at the second grill location at the center. Click on apply. And finally, I'll need a plane to view the hot and cold regions. So I'll create a plane, and make it horizontal. And let's view it at height, almost at the center. And we can hide case.foam. And to view the results, I had selected reconstructed case by default. So we just saw how to perform the simulation using CFD Forge for such kind of flow phenomenon, where cold air was rising up and hot air was going out through the CRAC. And the tool used was CFD Forge. So this tool was developed at CFD Baba Simulations Private Limited. And the motivation behind this tool was to simplify the OpenFOAM workflows, especially for specific applications. And you saw that in 7 clicks, we went from CAD to results. And the features are that you can import STL files, you can mesh it, you can set up the boundary conditions, run the simulation, launch ParaView without any core or mesh count limit. So there is no limit for mesh count or number of cores you can use. You can use as many cores as your PC has. And it is built using or powered by OpenFOAM and plus smart automation workflow. So why is it smart automation? Because you saw that we did not need to deal with any boundary condition names or any uh, other settings. We just simply selected all the things necessary, like uh, mesh settings, material properties, boundary conditions, and we didn't need to worry about any other files. So it automatically takes care of all the other files. And it is a licensed tool and it has expiry date. So this is a 1 year license right now, which I'm using. And all the rights are maintained by CFD Baba Simulations Private Limited. So next, uh, how can you get this tool? So anyone here who wants to try it can drop me an email at cfdbaba@gmail.com with subject CFD Forge Access, and you can get access to this tool on your own computer. You don't need to do anything extra. You just need to have OpenFOAM and ParaView on your system already installed. And even if you don't have it installed, I have a guide on how to install OpenFOAM ParaView from scratch. And then this CFD Forge is like another installer file. You simply need to install the setup by clicking next and then finish, and it will install CFD Forge in your system. And then you can access it with a license key. So, what after learning these skills? So, if you want to go in application side of CFD engineering, then you should have command on the tools that you are using. And if you want to go in the development side of CFD, then you need to have coding knowledge like C++, Fortran, and also Python can help for automation of tasks. And you should have a good portfolio in form of PPT and put your best complex problems. But before creating the portfolio, do at least 20 problems, different problems hands on, and just put the best problems in the portfolio. And when to use it, the portfolio, if you go to job interview, you can ask permission to show a portfolio of CFD projects which you have done. And most of the times, if your interview is online, you can screen share the PPT presentation and present it. And try to make it domain expertise. That means whatever field you choose, try to learn the theory in deep behind all the applications in that field, because in CFD you cannot do multiple applications at a single time. Once you join a company, you will mostly work within a certain range of applications, so make it domain expertise. And you should have these basic understanding of things like turbulence models, porous mediums, heat transfer, heat sources, multi-phase flows, a little bit about combustion if you know, that will help a lot. And you should have your LinkedIn updated and approach CFD professionals on LinkedIn. And how can you solve these 20 problems hands on? You can model them from papers. So we have research papers, which is what will help you to get the CAD model boundary condition and replicate it to solve the CFD simulations. So you can learn more at our website, cfdbaba.com. And I have uploaded lots of learning resources on my website. I can quickly show it to you once. So right now I just copy pasted this. However, I can type in and it will show me the link. And you can search CFD Baba on Google, get this website. And here, if you go down and click on Learn CFD, you can see I have uploaded lots and lots of resources for learning OpenFOAM as well as other CFD tools. And if you go to the home page, we have also started industrial CFD training where you will get exposure to the live industrial projects which are performed in industries. So you can go to this page and check it out. It is there on the home page. And finally, I'm very thankful to FOSSEE. It is always special to speak here because IIT Bombay is where my CFD journey truly evolved when I collaborated with FOSSEE and open source community. So thankful to all FOSSEE members for this community. And I want to encourage and implement usage of OpenFOAM in Indian CFD industry. And that's why I am sure that I can achieve this with help of FOSSEE, and I am always ready to offer all help and to collaborate with FOSSEE. And if you would like to contact me, I have this mail ID. You can note it down: cfdbaba@gmail.com, and follow me on YouTube, where I have almost 800K views now across the channel. You can connect with me on LinkedIn, where I have more than 16,000 followers, also on Facebook and Instagram. So, thank you for listening patiently. This is just an image of a lion which was simulated in OpenFOAM for external aerodynamics simulation, just to understand if the shape of lion is aerodynamic or not. And it turns out that the shape of lion is aerodynamic because the lift coefficient value was more than the drag coefficient value for flow over this line. So that's all from my side. And now we can have a Q&A and I will be happy to answer all your queries.
So there are some questions in the chat.
Okay,
Is
I will go through them. So this tutorial supports OpenFOAM or will work on ANSYS? Yes, it can work on any CFD tool. It is more about setting the correct boundary conditions and knowing the procedure, how to prepare your CAD model and how to mesh it to get required mesh to capture the flow phenomenon accurately. So I am taking questions and you can ask in the chat box if you have anything to ask.
so there was one. Okay, okay. Can I ask the
How
question?
much heat is generated in the data center that you have mentioned, or the wind turbine case?
Yes. So it was a volumetric heat source and heat was generating in that case. And that's why there was high temperature rise through the nacelle.
Are any values? How much heat was generated?
Yeah, as far as I remember, it was something around 120 watt, and that can be converted to watt per meter cube as per the volume of your heat source.
In the data center space?
Okay, in data centers, you are asking.
Both, sir. I'm asking both cases.
Yes.
How much?
So for data center, it is different. So from each rack, we were assuming around 1 to 2 kilowatt heat getting extracted. And accordingly, for this demonstration, I had simply set a hot temperature outlet at 40 degrees Celsius for the case. However, in reality, the rack can generate heat of 1 kilowatt up to 3 kilowatt based on the size of your server room.
So how much total heat was generated in the room, sir?
Yeah, so we were not able to conclude that study because of power cut. However, I will try to post the results. I'll run that again, and I'll take snapshots or video, and I'll try to post the results on social media on my LinkedIn. So please make sure to follow on LinkedIn. I'll post the results today as a summary of today's session. And there you can see all the temperature changes occurring. I'll also write a paragraph about this.
Okay, sir. And sir, you told that 2 to 3 kilowatt of heat was generated from a single server unit. So I'm
Mhm.
asking total server units that you were using in the
Yeah.
simulation. That would amount to like 10 kilowatt, maybe, if five server rooms are there, server units are there.
Yes, so in our geometry, there were just three server units in one rack, and there were total four racks. So I think there were only 12 units. However, I had combined all the faces, inlet and outlet faces of the three units in one rack, and that's why it was a single face.
No, I'm asking how much heat was generated. Like for 2 kilowatt, if we are assuming for single, then for 12
Yes,
units is 24 kilowatt, maybe, है ना?
yes. But in this case, like I said, it was not about the accuracy of the simulation. I just assumed 40 degrees Celsius coming out from the server room faces, rare faces, because that is what the temperature is generally, which comes out. It was a simplified case. Yes, and of course, the flow rate changes with respect to the heat load, and heat load also changes because the air is recirculating in the room. So that's why it is a fluctuating thing. And in reality, to simulate it, we need to enter the values in a table kind of format where we define how it is changing with respect to time or iterations, or if it is a function of temperature, that also can be defined.
Okay,
But
sir.
that all
And
is advanced methods. Yes.
how about, sir, going beyond simulation? If we have to decide for suppose 2 kilowatt, we have to give a cooling, and we have to uh, check whether which fan or fan cooling is provided. So CFM and all. Have you ever decided that rating and all? What CFM of fan can be used for this cooling?
Yeah, so the flow rate values which I used at the CRAC inlet and the uh, server rack outlets. So those were calculated from CFM, real CFM values, of course. But like I said, that was not the motivation behind creating this study. It was just to show the procedure from when you get to CAD until when you get the results, what all you need to do in between. So, all you are asking is the theory part, which can easily be found in many research papers. And also, there is a lot of experimental data where it tells you how the CFM changes with respect to the change in heat load of the server room racks, and they vary from geometry to geometry.
Okay, sir, I got it. And if assuming that temperature difference of 5 to 7 degrees there, and so for single degree of degrees, we have to provide different value of heat that we have to remove. Is it we have to multiply it for 7 times if say we have 7 degree Celsius difference?
No, we don't need to multiply it. If we separately specify the phases of the hot and cold server air inlet outlet. But right now, as you see, due to time constraint, I had selected only the combined phases. So all the phases of server inlets were one patch, and all the phases of server outlet was another patch. So in reality, you can model them separately, and then you don't need to divide anything.
Okay, thank you, sir.
Yes. So another question, is it possible to share this case study? Yes, once you mail me for the access to CFD Forge, this case study will also be shared.
Okay, so far, whatever Mr. Nikhil is explaining, are you able to understand? You can put a thumbs up in the chat, or you can just unmute and say yes, no. Because Mr. Nikhil is purely from a heat transfer background, so he has those applications like cooling and all of those. What strategy to use to cool the data centers and how to decide? Okay, wow. Okay, so see that in data centers, at least having a liquid cooling is a bit more difficult because you have electronics, right? So those fluids and all which are deionized and all of those, so they become a bit expensive. So that's why larger data centers prefer air cooled rather than liquid cooling. But if you want to simulate that, and you can do that, like you can take it up as a case study, and you can see the difference between a liquid cooling and the air cooling, and you can see whether the scalability is feasible or not. So that is one way you can do. You can then compare the data also, what you're getting, which one will be better. Obviously the liquid cooling will be better, but when it comes to scaling up, it will become a bit difficult. So in that sense, you can try to differentiate between both. Okay, what is CFD Forge 2412? So CFD Forge is something like a front end, you can say. In like now continuously in the previous workshops, you've seen that we were every time typing everything in our terminal. So the Forge part is like a GUI, you can say, in which like as Mr. Nikhil was demonstrating, he just added in the values he wanted. He just clicked a few buttons and he was able to make the whole mesh. Then he was able to complete the whole simulation and all. So it's just like a front end, you can say. Since it's air fluid model, so can we use this procedure for UAV and aircraft modeling? Now, in a UAV and aircraft modeling, you are typically solving Navier-Stokes equation only for your air. You only it's a single phase simulation. Okay, so I think Mr. Nikhil is facing some technical issues. Let's wait for him. In the meantime, as I was saying for Mr. Vimal, so if you are just trying to simulate a UAV or an aircraft model, it's a single phase, so you don't need to necessarily uh, distinguish between the air and like your fluid properties in two different terms. You can keep the whole fluid domain as air only, and you can simulate for that. It will be much more simpler. Like if you want to calculate something more like some particles or something, then you can use a multi-phase model. That would make more sense. But if you're just going for a single phase simulation, just going with air is fine. And okay, so there is one more question of suppose we have limited space in a large heat. So how do we decide cooling method? And now, like you can take this in terms of laptops and all. You have a very limited space and you have a lot of heat generation under load. So in those cases, sometimes the liquid cooling may be feasible, but again, it comes down to the costing and scalability. So if you have the resources and you are able to fit in a liquid cooling, you can go with liquid cooling. Obviously, liquid cooling will be much better compared to air in specific terms. Okay. Most of the time you find that air is much better than liquid. So it's a bit of a controversy right now. So you can choose irrespective of which one you are going with. You can choose either air or you can choose what liquid. And depending on how much heat transfer you want to do, like in a specific amount of time, how much heat you want to transfer from that particular medium to the environment, that also matters. So that is where your liquid air will come into play. Is it possible to share this case study? When Mr. Nikhil will join, we could ask him that. Yes, FreeCAD is open, so can you recommend any tutorial for that? So for FreeCAD, if you're starting off with FreeCAD, there are multiple YouTube tutorials. You can just type FreeCAD tutorial beginner and you can go ahead on YouTube and learn that. It's not a big deal. We do have FreeCAD under the FOSSEE banner as well, and it's still in the preliminary stages. So we can, like in the future, you can expect some FreeCAD tutorial, like the spoken tutorial that we have for OpenFOAM. Can we use jet cooling? Uh, by jet cooling, what exactly do you mean? In what sense? Could you elaborate a bit? Okay, impinging cold air into the heat system. Now, if you want to do something like that, you if you want to simulate something, you can do that, obviously. You just have to change a few boundary conditions. Like if you have that inlet condition, like in Nikhil sir's case, you are giving some heat, you're giving some inlet from the bottom and you're taking an outlet from the top. So in that sense, you can just change the boundary conditions and you can implement that jet boundary condition. So there are multiple ways to do that. So you could try that as well. Okay. So there was one question previously. I think when you disconnected, it was there. So there was one participant asking whether liquid cooling, liquid cooling, how do you decide which liquid is best for cooling? And if you have a specific area constraint, how do you decide between air cooling and liquid cooling? So that was the question. So could you answer that?
Yes, liquid cooling is very expensive because it has lot of maintenance. So usually it can be used for small, medium scale projects, but for large scale projects, usually air is used because it is much cheaper and more proven way because it has been used from many years now. But liquid cooling is a relatively new concept and leakage is the main problem in liquid cooling and that requires a very high maintenance.
Yes, sir.
So it varies from application and budget of the project.
Yes, sir. But I think the question was more relevant towards if you want to simulate such a thing, what criteria would you satisfy for liquid cooling?
Okay, for simulation.
Yes.
So first the CAD model needs to be appropriately modeled as per the fluid domain. It should be watertight. And then you can assign different fluids. Suppose if you are using water or another coolant, you can define it. And if you are using air above it, then you can also define air as the another material. But once you define two materials, it becomes a conjugate heat transfer problem. So you cannot solve that kind of simulation in bind simple form. It is for a single material. So for multiple materials, you can use solver named CHT, multi-region simple form for doing steady state simulations, or CHT multi-region form for doing transient simulations.
Okay, sir. Thank you, sir.
So there was also one question that the force run the scope of force run is only limited to buoyant foam, or it can run multi-phase as well.
Yes, so CFD Forge is a custom tool which is developed for specific applications. So the tool which I demonstrated was bind simple form, which can be used for any CAD model to simulate flows which have buoyancy in them, like in this case which we saw today. So CAD model can be anything. We also simulated the flow through multiple outlet pipe using same solver. So CAD can be anything as long as the physics is incompressible flow with heat transfer, and turbulence is also considered. And similarly, I have different versions of CFD Forge, like I have CFD Forge Simple Foam, which you can use to solve external aerodynamic cases for subsonic flows, or you can even simulate internal flows using it for flows where we don't have heat transfer. So similarly, we have by CFD Forge Interfoam, which solves for multi-phase flows. So for each uh, application or for each solver, we have a different version of CFD Forge.
Okay, sir. Thank you, sir. Okay, so for people who are asking about HVAC systems and room cooling and all, we have a session in the afternoon. So that time we can take up those types of questions. So if you have any questions for Mr. Nikhil regarding the CAD generation or something related to his cases that he's just showed us, you can ask those.
Actually, I have a question for Mr. Nikhil.
Okay.
So, yeah, Mr.
Yes,
Nikhil,
Pahilwan.
yes, this CFD Forge that you just talked about, this is a licensed software, you said. So people have to
Yes.
pay for it. Is it a payable thing or how is it?
Yes, it is a licensed software with 1 year license validity, and
Mhm.
currently it is available only for companies and industries. But soon
Okay.
it is going to be made available for students as academic license, and then they will be able to use it for a limited period of time for free. So
Okay.
yes, it is going to be provided for free
I was curious
once
about
we
that
have.
only.
Yeah, the academic version always needs to be there, otherwise, how will students access it? So, of
Yes,
course, I
yes,
have
yes.
thought about it. And yes, the people who mail me for CFD Forge access, I will send the link to access the software for a limited period of time for free.
How much
It
free
will
time?
be
1 year, I think.
one
1 month.
month period.
Okay, okay.
Yes, 1 month would be enough to run many simulations because, as you saw, the tool is quite fast and you can quickly run multiple cases on it.
Another
I
question has
s-
come.
yeah, I see this. Is there any way to couple star CCM with OpenFOAM? But I don't know why you would want to do such a thing. This is quite a funny question.
Sir, there is also another question regarding CFD force that it can be
Mhm.
used for overset topology.
Not right now. We have not added the option, but if you have observed properly, you will understand that you can modify any file in any folder. You have full access to all the OpenFOAM files. So if you can know the settings of your overset mesh, then of course you can just add those settings in your case and run it. And it will just run normally, like we changed the velocity and temperature boundary conditions. Similarly, you can change anything in the case and run it. So it is not a black box at all. Access of all the files have been given to the user.
Thank you so much, Mr. Nikhil, for being so patient and explaining many interesting things, many new things that will be very useful for the students as well as faculty members as well as CFD professionals. So it was a
Ye-
wonderful session, sir. Thank you so much.
Yes, I said I'm also very thankful for the opportunity provided by IIT Bombay, and I'm always happy to come and share my knowledge here.
Yes, yes, yes. Yeah, we know that, and we are very much thankful to you. So
Yeah.
if in case they have any further queries, they can directly write to you or they can write to us and then we can direct it to them.
Yes,
Yes.
yes, sure, Pal.
Okay. Thanks a lot, sir. Thank you so much.